Hello there and welcome back to this video series on control systems. In the previous video, we have studied direct analogy, that is force voltage analogy, which is an electromechanical analogy in which force is considered to be analogous to voltage. Similarly, we have analogous quantities for other properties, that is damping, spring, and mass. We have also seen what we mean by scale factors for voltage and current. That is, if the voltage tends to be too high, if the force is too high, the voltage will be too high, which is again difficult to handle. So we have a scale factors by which a small voltage represents a big force. Similarly, a small current can represent a large velocity. We have studied such aspects in the previous class. After watching this video, uh, you'll be able to specify what we mean by time scaling, what is the purpose of such time scaling. It would be best if you watch videos 16, 17, 18, 19, 20, then 21A, 21B. Before going into this class, you can make the best out of this. It will be crystal clear to you. Quickly go over this force voltage analogy or direct analogy to reinforce your memory and understanding so that you can glide very smoothly into the present class. We have seen one electrical system, which is shown here, resistor, inductor, capacitor, all put in series. Similarly, there is a mechanical system where the damping B, the spring the K, and mass M, they are in parallel. That is series parallel connection between these two analogs. This is the electrical system, this is the mechanical system. That is why we call it force voltage electromechanical analog or direct analog, okay, in which force is analogous to voltage, and then mass is analogous to inductance, resistance is analogous to damping, reciprocal of capacitance is analogous to spring, and displacement is analogous to charge. It would greatly help if you remember this table thoroughly. We have also seen that if you want to reduce the voltage by a factor KE and the current by a factor KI, the inductor, resistance and capacitance values are given by these Rn, Rb, 1 by Rk, where R is Ki by Ke. With the scale factors Ke and Ki, we also have one other aspect. That aspect is time scaling. Certain systems are very slow. For example, if you are experimenting with creep, mechanical creep is very slow, maybe about a millimeter in a week or maybe even slower. Such systems, when we use to build analog, if we build analog of such a system, the electrical system also will be acting very slow, extremely slow. Okay, it takes a week to complete an experiment. Such would be a waste of time. In such case, we want the electrical analog to be very fast. So if we want to study the phenomenon of creep and how things are behaving in a mechanical system, we can build an electrical network consisting of R, L and C, wherein the electrical system's dynamics are very fast. So you can complete the experiment very quickly. Similarly, when the mechanical system is very fast acting, such as the vibration of a turbine blade tick, if you use the electrical analog with the same time scale, you hardly find any time to observe minutely. In such systems, we want to slow down the electrical analog. So when the mechanical analog is very slow, you want to make it a bit fast. On the other hand, if the mechanical system is very fast, you want the corresponding electrical analog to have dynamics in such a way that we can see it clearly. I'd like to show in a kind of picture wherein we have a mechanical system which is very slow acting. So conducting experiments on it will be very slow. It may take hours and days. For such a system, we want to build an electrical analog which is fast acting. So experiments could be replicated with exact dynamics very quickly in electrical system. To achieve this, for slow acting systems, to speed up the dynamics, we have what is called a time scaling. We will try to see what is this time scaling. To do that, we will use symbol T to indicate the time it takes for a phenomenon to occur in the mechanical system, which is an actual system, mechanical system, for which we are building an electrical analog, and in the electrical system, let tau be the time taken for the corresponding analogous phenomenon to occur. With these two things, we can clearly see the relationship. If t is very small, that is for an event to occur in the mechanical system, it takes very small time. That means the system is faster. If t is larger, that is time taken for a phenomenon to be large, then we say the system is slow. The same thing we can say here. If tau is very small, electrical analog is faster. If tau is very large, we say the electrical analog is slower. To indicate the relationship between the t and tau, we use a factor called a, okay, and define that tau is equal to a multiplied by t greater than 1. When a is greater than 1, t is smaller. When t is smaller, actual system, that is the mechanical system, is faster and analog system is slower. Similarly, when a is less than 1, when a is less than 1, t is large, so the original system is slower. This you need to very carefully remember. When a greater than 1, analog system is slower. When a less than 1, the original system is slower. As usual, we need to choose voltage and current scaling factor such that F is equal to Ke into E, velocity is equal to Ki into I. To find the values of the resistor, inductor and capacitor to give us a scale factor of Ke, voltage scale factor of Ke, velocity current scale factor of Ki, and a time scaling to change the speed of response of mechanical system and electrical system. We'll try to find these values. We'll try to write the equations, three equations, scaling equations at one place, and note that all the derivatives in the mechanical system are with respect to t. All the derivatives in electrical system are with respect to tau. That is because we chose t to be the time for mechanical system, tau to be the time for electrical system. So derivatives in mechanical system will be in terms of t, derivatives in electrical system will be in terms of tau. With this, we consider the three quantities, that is the mass, the damping and the spring stiffness, and try to relate them to L, R and 1 by T. Just as we have done in the previous case, We'll try to consider each row in the table and write down one equation. From row 1, we have F by E, which is voltage factor, is m d square x by dt square by L di by d tau. You can see T here for mechanical system, tau here for electrical system. This would simplify to Ke is equal to mki by L into 1 by A. That is L is equal to A into Ki by Ke into M. Similar thing we can do for row 2, that is for damping. F by E is Ke, B dx by dt Ri. So B Ki by R, Ke is equal to B Ki by R, so R is equal to J. By a similar exercise from row 3, we can find capacitance is equal to A by Ki Ke K. When we are trying to build an analogous system that gives a voltage scale factor of Ke, current scale factor of Ki, and the time to be adjusted by an equation tau is equal to At, we can have L, R and C values as given by equation R is equal to Ki by Ke. So you have L is equal to ARM, R is equal to RT, C is equal to A by RK. We will see one simple problem to explain the concept of this time scaling and to give us a intuitive feel. The parameters of mechanical system are M is equal to 10 kilograms, B is 5000 Newton second per meter, A is 2500 Newton per meter, and we have maximum force as 500 Newtons and maximum velocity as 5 meters per second. We need to have an electrical analog with maximum voltage 100 volts, maximum current 10 amperes, and we want to find what size inductor capacitor to use when we want to speed up the electrical analog by a factor of 10. We'll try to slowly go through this problem. To propose a solution, we see that Ke is F over E, which is 50. Ki is x dot by I, velocity by I, that is 0.5. Hence, R is equal to Ki by Ke, 1 over 100. Thus, you have A is equal to L is equal to R times M, C is equal to 1 by Rk, R is equal capital R resistor is equal to R times B. This is a straightforward case when there is no time scale. In part A of the question, time scaling is not asked. In the second problem, you are asked to find slowing down. Because if you are trying to if you are trying to speeding up by a factor of 10, you have A is equal to 1 by 10. Hence, you have L is equal to ARM, capital R is equal to R times B, C is equal to A by R K. Carefully go through this problem once or twice. If you have questions, you can always ask me. So, in summary, if we have a situation where voltage needs to be reduced by a factor of Ke, current to be reduced by a factor of Ki, and we need to have a time scaling given by tau is equal to A times T, where T is the phenomenon or time required for a phenomenon to occur in mechanical system. Tau is the time required for the corresponding phenomenon in electrical system. Then we have the three equations for inductance, resistance and capacitance are given by L is equal to A times R times M, resistor is equal to R times B, capacitance is equal to A divided by R times K. That's all we have for now. Have a great day.